In Chapter 3, we've now finished our discussion of chemical equations, or our introduction. We've talked about at least a majority of the classification of reactions. We've gone over formula weights, the mole, empirical formulas, and we're now ready to finish off with our stoichiometry and limiting reactants. So stoichiometry problems involve the use of chemical equations to identify amounts of either products or reactants based on amounts of other products or reactants that are provided for us. So for instance, in this equation, which describes the reaction of hydrofluoric acid with silicates, sodium silicates in glass, in which the silicates are broken down by the hydrofluoric acid. We are starting with, or we're told that we're starting with 0.33 grams of hydrofluoric acid. We aren't told anything about the sodium silicate, so we must be assuming that that's an excess, which would make sense. If this were stored in a bottle, there would be excessive amounts of the sodium silicate. It wants us to determine the milliliters of water produced by the complete reaction of the 0.33 grams of hydrofluoric acid. We're going to take our hydrofluoric acid that we start with, put that over 1. Now the ultimate goal, or the preliminary goal of this is, in order to get from the hydrofluoric acid to the water, we utilize the coefficients in the equation, the 8 and the 2. In order to use those, we need to get to moles. So we're going to go from grams of hydrofluoric acid to moles of hydrofluoric acid. And so if we look at the periodic table, we see that 1 mole of hydrofluoric acid is going to be 20.0 grams. So that gets us into moles of hydrofluoric acid. And this is where we can utilize the balanced equation. If we look at the balanced equation, we know that 8 moles of hydrofluoric acid will produce 2 moles of water. Now, once we're in the moles of water, we can now go to the quantity of water needed. So from moles, we're going to go to grams, and then use the density to go to milliliters. So 1 mole of water is 18 grams of water. And using the density of water, 1 gram per milliliter, 0.0 grams of water, 1.0 milliliters of water. Multiplying by all the numbers on the top, dividing by all the numbers on the bottom, we end up with 0.074 milliliters of water produced. Taking stoichiometry problems a step further, limiting reactant type problems. I should say, back for a moment, stoichiometry problems, there's a lot of different amounts of substances we could start with. We could start with volumes of solutions. We could be asked to figure out the volume of gases. So we need to be somewhat flexible in dealing with stoichiometry problems, utilizing all the skills that we've developed. In the limiting reactant type problems, you'll notice that here in the reaction of ammonia and water, the information we're provided with is both the amount of the ammonia that's going to react, or that we're putting in the reaction chamber, as well as the amount of oxygen that's present. Now, obviously what will happen here, or maybe not so obviously, but one of these is going to run out first. Right? So the first thing we're going to have to do is determine which one will run out first, or in other words, the technical term we use for that is the limiting reactant. And all we do there is we choose one of them and figure out how much of the other one is needed. So I'm going to start with the ammonia and say that, all right, well, if 1.50 grams of ammonia reacts, I'm going to try and determine how much oxygen is needed. So I'm going to be going this way on the balanced equation. So again, if I'm going to use the equation, I need to get to moles. So I'm going to go from grams of NH3 to moles of NH3. And periodic table tells us that 1 mole is 17 grams. Next, we'll use our balance equation, which describes or tells us that 4 moles of ammonia will react with 5 moles of oxygen. In order to compare with the oxygen, we need to get to grams. So we would do 1 mole of oxygen is 32 grams of oxygen. And again, if we do our calculations correctly, we end up with 3.53 grams of O2. And then one little phrase here that's going to help us with our understanding, needed. Right? So this is the amount of oxygen that is needed. Now we're going to compare the amount that's needed with the amount that we have. And you can see that we don't have enough oxygen. This tells us that the oxygen is our limiting reactant. And the ammonia is our excess reactant. So that's the one that's going to be left over. So we're going to use the limiting reactant, the oxygen, to determine how much of our product will be formed. 1.85 grams of O2 will definitely react. Again, I need to get to moles, so 32 grams of O2 to 1 mole of O2. Five moles of O2 will produce 4 moles of nitrogen monoxide, NO. And in this case, the problem is asking to figure out the number of grams of the NO produced. So we're going to go from moles of NO to grams of NO. Again, looking at the periodic table, 14 for nitrogen, 16 for oxygen. We have 30 grams of nitrogen monoxide to 1 mole. We do our math, and we end up with 1.39 grams of NO produced. The last part of this problem wants us to determine the amount of excess reactant that remains after the reaction is complete. So if you recall, the ammonia is the excess reactant. So what we're going to need to do is take our limiting reactant, our oxygen, and determine how much ammonia is needed to react with all of that oxygen. So we start again with our 1.85 grams of oxygen. do our grams of oxygen to moles of oxygen. We look at our balanced equation. 5 moles of oxygen react with 4 moles of ammonia. One mole of ammonia has a mass of 17 grams. And this leaves us with 0.788 grams of ammonia, and again that one little word, needed. So at this point we compare that amount needed with the amount we have, which you recall is 1.50 grams. So we have 1.50 grams of ammonia. We need 0.788 grams of ammonia, which leaves us then with 0.71 grams of NH3 left over. So for this question, that would complete our limiting reactant problem.